Hello friends, welcome to our channel Physics for You, and in this video we are going to discuss about the Sommerfeld quantum model, or we can say it as Sommerfeld quantum theory, or simply sometimes people say Sommerfeld model. Okay, so if you are aware that we are under the heading that free electron theory of metals. So whatever we are whatever we are discussing from previous 3 or 4 videos, everything it is related to the metals and moreover the free electrons present in the metal. So if you remember in the very first video, that is of Drude-Lorentz theory, it is also called as the Drude-Lorentz classical theory. So in that theory, or according to that theory, we have a number of free electrons in the metal, and according to Drude and Lorentz, or according to that classical theory, yes, what Drude-Lorentz proposed is that according to, I will say, or I will call that as a classical theory. According to this that classical theory, the free electrons obeys MB distribution. If you remember, MB distribution. So MB distribution means Maxwell-Boltzmann distribution. Okay, but yes, this Sommerfeld came and he just added the things into this model, and he has proposed his own model, and he said that no, these free electrons cannot be studied using this MB distribution. We should go by the quantum approach, and we should follow the Fermi-Dirac distribution of particles. Fermi-Dirac distribution. So here, that is what the major correction done by the Sommerfeld, and Sommerfeld said that we should follow the Fermi-Dirac distribution to understand the behavior of free electrons within metals and to study all the things regarding that particular free electrons. Okay, so according to this Sommerfeld, an electron in a metal finds itself in the field of all nuclei and all other electrons. So there are number of electrons, and when we are dealing with a particular metal, so we have n number of atoms, and within one particular mole of we have 10 raised to 23 number of atoms, that is Avogadro number of atoms, right? So what Sommerfeld said, if I am talking about a specific electron, now let us consider I am talking about this electron. So this electron is in the field of several number of nuclei which are positively charged, and more or other electrons which are negatively charged. So the potential energy of such an electron may be periodic, because number of electrons and number of nuclei are surrounded or by the particular electron. So Sommerfeld in his model assumed that the potential energy is constant everywhere inside the metal. So according to this Sommerfeld, everywhere, if I am talking about the potential energy, it is constant within the metal. It is constant everywhere within the metal. Now if I am talking about a metal surface, and now let us consider this is the metal surface, and here we are saying that the potential energy is constant. Okay, but when we observe carefully the emission process, so we know that until and unless I supply heat energy to this particular metal, it is not able to, or the electron is not able to jump outside the metal. Yes or no? That means what? At the room temperature, it is not possible to have the emission of electrons, which is the rest inside the metal. Okay, and therefore it is obvious that the potential energy inside the metal is not only constant, but moreover it can be considered as a zero. The potential energy is zero, because if that electron has to be ejected from the metal surface, it requires much more energy at room temperature, right? It requires much more energy, or moreover the potential energy. So we can consider that electron present in metal at room temperature, or a steady electron or a rest electron, is having the potential energy nearly equal to 0, or almost we consider it is equal to 0. And to take the jump outside this metal, it requires tremendous amount of energy, and that we can consider the infinite energy potential. That means that can be taken as a one-dimensional box. Now whatever may be this metal, we can treat this as a 1D box. I think you have heard this name somewhere. So this is considered as a one-dimensional box where potential inside the box is 0 and potential outside the box is infinite. So this is how the idea came about the infinite potential and zero potential, because we can see at the room temperature electron cannot eject outside the metal. So that means for that electron, if I am talking about the electron present in a box, so it can be considered as electron trapped in a potential well. This is also known as potential well, 1D potential well, one dimensional potential well. So the electron is trapped in one dimensional potential well where inside the potential is 0. That means to stay there, electron does not have to spend something or some energy or something. But if the electron has to jump outside the box, yes, it requires this much amount of energy. So therefore, or it is not possible to jump out at the room temperature, and that's why with respect to that electron energy or with respect to that zero potential energy inside the box, we can treat the outsider energy is infinite energy. Okay, so having infinite energy means it is not that the infinite is a number and this much is the energy. So taking infinite energy means as compared to the energy inside the box, the energy outside the box is very large. Or for this electron, if it has to jump outside the box, it requires a very large amount of energy as compared to this zero potential energy. That's why we can consider ultimately we can say the electron cannot jump outside that box, and therefore the energy may be outside the box, might be it is infinite energy. That is how the what we can say the idea of the potential well or the box, one dimensional box, has came into the mind. Okay, so thus the interior of the metal box is represented by the potential energy box, more or one dimensional potential energy box. It is also known as potential well. So in this model, the electrons are assumed to be valence electrons of the composing atoms. So yes, obviously free electrons, or we call it as valence electrons. So for simplicity, let us consider an electron limiting to the remain within a one dimensional crystal of length L. So I have drawn the diagram below. So for simplicity, what we are considering, it is simply a one dimensional box, one dimensional crystal whose length is L. Okay, here we can say at x is equal to 0. I am talking about one dimensional means yes, only one axis, x equal to 0 and x is equal to L. Okay, so this is what is simply one dimensional box or one dimensional crystal we can consider, right, of length L. Let the potential energy everywhere within the crystal is constant and is equal to 0. That's what I said. And now let us consider at the two ends of the crystal, the electron is prevented from leaving the crystal. Yes, obviously it is not possible to jump outside the crystal. So we consider a very high potential barrier or high potential energy, and that is nothing but V0. Let us consider that. Okay, right. Now this is what V is a potential energy, and if I am talking about the total energy, it is represented by E. Okay. Now for this case, if I have to write, or if we have to write the Schrodinger equation, because we know that this can be explained by using the Schrodinger equation. And yes, how can we write the Schrodinger equation for this particular condition or system? So yes, the Schrodinger equation for this system we can write in one dimensional case as d2 psi by dx square plus twice m by h cross square e minus v of x psi is equal to 0. This is general form, okay, not for this particular case. So this Schrodinger equation general form in one dimensional can be written for our case as simply here the if I want to talk about the inside the box, the potential energy is 0. That's why this term should go vanish, and therefore the Schrodinger equation within box or within the range, we can say 0 is less than equal to x is less than equal to L. It is like this. This V is 0. Therefore d2 psi by dx square plus 2me by h cross square psi is equal to 0. Or again we can write this particular bracketed term 2me by h cross square as omega square. Okay, here we know that psi is a wave function. If you don't know, if you have a little bit learn about the quantum mechanics, then you know psi is a wave function. Okay, and what I'm talking about in yes, potential energy is the total energy, V is potential, psi is a wave function, and this equation is known as Schrodinger wave equation. Okay, right. Now therefore we got a simplified form of the Schrodinger equation inside the box. So if I want to specify, so I will specify here inside the box, inside the box. So inside the box, shall I write limits like this? 0 is less than equal to x is less than equal to L. Yes, this is what the, we can say, the limiting conditions inside the box. Means say the particle is trapped within the limits 0 to L, and for that we got the Schrodinger equation and we named it as equation number 1. Okay, right. And yes, just for simplicity we have written 2m e by h cos square as omega square. So that is what for our simple calculation purpose only. Okay, and now for this equation number 1 we have a solution. The general solution we can write like this: psi is equal to a into e raised to alpha x. So just this is how the method to solve the differential equation. Now yes, equation number is equation number 1 is a differential equation. Moreover, Schrodinger equation is a differential equation. Moreover, second order differential equation. And how to solve this second order differential equation? Simply take a general solution or what we can say, a solution, and let us check whether it is satisfying the equation or not, and therefore we should keep psi here also. So this psi we have considered a general solution. Psi is equal to a e raised to alpha x. Let us substitute that values in equation 1. That means first of all we will find d2 or d psi by dx, and then d2 psi by dx square. So therefore for this psi I want double derivative, so we will just differentiate equation 2, that is psi with respect to x twice. So after differentiating once, what we get? D psi by dx derivative of left hand side, and on the right hand side a into a is constant and derivative of e raised to alpha x is e raised to alpha x. And yes, but the derivative of this alpha x is alpha, therefore we have multiplied with alpha. Okay, so d psi by dx is equal to a alpha e raised to alpha x. Now one more time we have to take derivative, so therefore left hand side derivative of this equation now d2 psi by dx square is equal to, again a is constant, here alpha is again constant, derivative of e raised to alpha x is e raised to alpha x, and one more time by the chain rule derivative of alpha x is alpha. So already one alpha is here, so alpha into alpha, alpha square, and a e raised to alpha x as it is. Now let us substitute these values of equation 3 and yes, obviously equation 2 in equation 1. So therefore equation 1 becomes what is whatever may be our Schrodinger equation is this equation 1. Let us substitute these two values 2 and 3 in equation 1, and yes, to the left hand side equation 1 d2 psi by dx square. So now d2 psi by dx square is nothing but your equation number 3. Substitute that value, so it is alpha square a e raised to alpha x plus omega square. Okay, I have written here instead of 2m e by h cross square omega square, and what is psi value? Psi is here a e raised to alpha x, and right hand side as it is 0. So let us try to cancel the things. What will get cancelled? This complete a e raised to alpha x, a e raised to alpha x will get cancelled to the right hand side, and alpha square plus omega square equal to 0, or we can write it as alpha square is equal to minus omega square, and after taking the square root we got these roots. We can say alpha is equal to plus or minus I omega, because here or I can write alpha is equal to under root minus omega square. Moreover here it is plus or minus, but this minus in the under root we know it is imaginary, so imaginary one, so plus or minus under root minus 1 omega, and that under root minus 1 we know we called it as imaginary number I. So that is what alpha we got here. Okay, so let us substitute this value of alpha in equation 2. That is what the general method to solve any differential equation. First of all, consider the solution, substitute that in the differential equation, take the roots, and again resubstitute the roots in the solution whatever you have considered. So here we have to write the roots, or we have to substitute the roots in term instead of alpha, but we have two values of alpha. That's why we will substitute first value plus some constant into the second value, and therefore the solution becomes, so generally it was what the solution, I will write equation 2 psi is equal to a e raised to alpha x. This is equation 2, or this was equation 2. but here we have two values of alpha, so therefore I will post first value a into e raised to first value, that is I omega plus I omega, right, plus some constant b into e raised to second constant second root, that is minus I omega x. So this is how we can write the solution for a differential equation. But again we know e raised to I theta, e raised to I theta, or moreover e raised to plus or minus I theta is equal to cos theta plus or minus I sin theta. Okay, now let us use that and we get this e raised to I omega x as cos omega x plus I sin omega x, a constant as it is, plus b constant as it is, e raised to minus I omega x, we can write b into cos omega x minus I sin omega x. Now let us take the common things, because if we multiply with this a to both the terms, and after multiplication of b with these both the terms, we can take the constant, we can take the common. So here cos omega x and cos omega x is common, and the additive terms will be only a plus b. So a b into cos omega x, plus again similarly here sin omega x and sin omega x is common, and I is also common. So I sin omega is common, and from this we can write a, and from this but with minus sign b, a minus b I sin omega x, or you can increase one more step here, a cos omega x plus a I sin omega x plus b cos omega x minus b I sin omega x. Now also you can take the common, nothing else, right? Very simple step. Now let us consider, instead of this a plus b, we will write one another constant c1 for simplicity, and instead of a minus b we will write c2. Okay, now finally let us substitute the value of omega. Omega is not what we have any quantity, but simply we have considered for the simplicity. So substitute the value of omega. If you remember, we have considered omega square is equal to 2me divided by h cross square. So therefore omega will be under root 2me divided by h cross square. So substitute the value. So c1 cos under root 2me h cross square into x. Now this x is outside the square root, plus but inside the theta. Okay, see here, plus c2 sin under root 2me by h cross square x. Similar. So this is what the general solution for our Schrodinger equation, which is for the electron or the particle present inside the box. So let us name it as equation number 4. So here the constant c1 and c2 can be calculated by using some boundary conditions, because at x equal to 0 and at x equal to L, the wave function vanishes or wave function is continuous, right? So using that boundary conditions we can find the values of c1 and c2. But before that, before investigating that boundary conditions, consider the form of Schrodinger equation on either side of the crystal. Okay, that means I will draw here the one-dimensional box like this. This is what the potential barrier of potential V0, and here inside the potential well it is 0. So just we got the wave function inside the box, but what about this and this? So that for that we will just talk about, and then we can find the values of C1 and C2. So here after considering the regions where the potential energy is large, that is what for means outside the potential well. So including the potential energy term, because V0 is the potential outside, we can write the potential Schrodinger equation for the particle which are present outside the box. So this is what the we can write wave function, Schrodinger equation. So the Schrodinger equation, d2 psi by dx square minus twice m by h cross square V0 minus E, because here now V0 is greater than the energy of the electron, and therefore we should subtract this. That is, this is the condition, V0 is greater than E. Earlier inside the box, energy of the electron is, or energy of the particle is greater than V, because V is 0 only. So there is no problem about the whether get greater or less. But when we are outside the box, then here V0 is greater than E. So here we cannot write E minus V0. So we have to write V0 minus E, and therefore here it is a negative sign equal to 0. This is the Schrodinger equation outside the box, right? Now we can write the general solution in analogous manner to this equation for V0 is greater than E, and that will be as we have written for this C1 and C2 constants. So here I will write the C3 and C4. So psi is equal to C3 exponential of under root 2m V0 minus E divided by h cross square x plus C4 exponential of minus under root 2m V0 minus E divided by h cross square into x. So this is what the general solution for the case or for the outside the box. I will write here, it is for the outside the box, outside the box. Moreover, in case of now from this equation we can clearly say as x increases, whether it is increasing in positive or negative manner, this psi is going to be increased, the psi is going to be increased. That means I can write here as x increases, whether it is positively increasing or negatively increasing, this consequently this psi is increasing, this psi is increasing. And as we say as x is tending to infinity, if let us consider x is tending to infinity, then the psi is also tending to infinity, and psi is tending to infinity means there is a maximum probability to find the particle. Actually this psi represents psi don't directly represent, but depends on psi we have the probability density, and if we are saying the psi is increasing, ultimately probability density is increasing and ultimately the probability is increasing. But when we are saying that the x is tending to plus or minus infinity, psi probability is also tending to infinity, and which is certainly not possible because probability should be finite. We cannot talk about the infinite probability. Okay, so this is what the contradiction we are getting, and consequently the consequences of this will get the two different solutions, because at C3 is 0 among this equation 6, or from this equation 6 C3 will be 0 when x is greater than equal to L. That means here one more time I will draw the well here, here is L, here is 0. So in this region C3 will be 0, and in this region where below the x0 or below the 0 or to the left hand side, it is here C4 will be 0. Now if we substitute here in equation 6, so for those two different regions we will get the two different solutions, right? So obviously from equation 6 only, once C3 is 0 and once C4 is 0, and therefore for x is greater than equal to L, means for this region we will get this equation number 7 as a solution, and for the this region below the 0 we will get the size is equal to C3 exponential of under root 2m V0 minus E by h cross square x. This is what the two different solutions for the two different regions. Okay, so guys, this is not the end of this particular Sommerfeld model. Again we can have the, or we will have the video of 20 to 25 minutes and then it will finish. So instead of making the lengthier video, I think we should stop here and we'll meet in the next video with the continuation of this particular model, that is Sommerfeld model. So till then I suggest you please study thoroughly, watch this video carefully, write each and every step, and if you have any doubt please post in the comment box. And yes, if you feel this is value addition to your knowledge, then like our video, and for more such videos subscribe to our channel and share with your friends, and obviously press the bell icon so that you will get the notifications as soon as I will post my next video. Thank you friends, keep learning and take care. Thank you.